Alrighty guys, welcome back to another little video. In this one I'm going to be talking you through the solutions to this exam problem that I put out the other week. So this exam problem all relates to statistics, and specifically in each question you need to be thinking very carefully about which statistical information you're going to be reaching for. So in this first question we are told that doctors are studying resting heart rate. So this is the thing that we're interested in here. Heart rate is measured in BPM. So we should be thinking, okay, BPM, that can really be just about anything, including decimals, so this is going to be a continuous variable. We're told that the mean is equal to 68 BPM and the standard deviation is equal to 8 BPM, and we want to find the probability that a randomly selected adult has this resting heart rate. If we read this question, we can also see that the heart rates have been normally distributed, so this is relevant to the question as well. Okay, so what we can say is, for example, we're going to introduce a variable. This variable is going to be our continuous random variable. And the thing that we're interested in here is heart rate. So we can say that let x equal the heart rate. And we're interested in here whether or not the probability that the heart rate, so the probability that x is equal to, well, the question is telling us that we want the probability to be between 60 and 90. So what is the probability that x is greater than 60 and less than 90? It's effectively the question here. The way that we can work this out is, given that we're dealing with a normal distribution, we're going to jump over to the CAS calculator. We're going to go interactive distribution, continuous, and normal distribution, and we're dealing with a normal cumulative distribution, so that's CDF. When we're dealing with inequalities, it's always CDF. For a single value, it is PDF. So let's jump across here, select that. Just double checking I am recording audio. Yes. Okay, so we put in 60 and 90 as our lower and upper bounds. Standard deviation is 8, and mean is 68. So we get that. So using we'll write it out. So binomial CDF with a lower bound of 60, upper bound of 90, standard deviation 8, and mean of 68. And that comes out as being equal to 0.838, correct to 3 decimal places. Awesome. All right, moving on to the next question. We have here a lot of context. Sometimes with these questions, it's better to start with the what the question's actually asking and then work our way backwards. So here we're interested in what's the probability. So the probability that H given S. Now, what are H and S here? Well, it says here H is the event that a randomly selected adult has a slow heart rate. So what's the probability that they have a slow heart rate, and given that, that they are playing sport regularly? The way we're going to set up a conditional probability question like this is we're going to just use the formula. So it's basically conditional probability is H given S divided by the probability of S. So these are the things that we need to work out. Now let's jump back up and read the question. So we're told that someone has a slow heart rate if X is less than 60. So we've defined X up here. So probability that's less than 60. We're told that the probability that X is less than 60 is equal to 0.1587. So this is the probability that somebody has a slow heart rate. It's known that 29% of adults play sport regularly, and it's also known that 9% of these adults play sport regularly. So what are these things? So this 29%, that is the probability that someone plays sport regularly. So that's the probability of S is 0.29, and also the probability of that they play sport regularly and they have a slow heart rate. So that is H and S is equal to 0.09. These are the things that we need to answer the question. So that's probability of H and S occurring is 0.09. So that's this result here, that they play sport regularly and have a slow heart rate. And then this 29%, that is the probability that they play sport regularly. So 9 over 29, what's that equal to? So I've got to set to decimal, 0.09 over 0.29, hit enter. That comes out as about 0.310 to 3 decimal places. Yep, awesome. So moving on to the next question, what is the probability Sorry, this is about independence. So are the events H and S independent? First up, what does independent mean? What this essentially means is that the probability of the first thing succeeding or failing does not affect the probability of the second thing succeeding or failing. So putting this into words, we're asking here, does having a slow heart rate depend on whether or not you play sport regularly? That's essentially what the question's asking. And the criteria for this to be true is that the probability of H given S, so the probability that someone has a slow heart rate given that they play sports regularly, needs to be equal to just the probability that they have a slow heart rate. That's essentially what the question's asking. Because whether or not they play sports, if that has an impact on what their heart rate is, then that means that they're not independent of one another, are they? Like if the probability of me tossing a heads, given that I tossed a tails on the previous round, well, it's still just equal to the probability of me tossing a heads. So is this true? That's the question that we're asking. Well, we can see in the question that the probability that someone has a slow heart rate, that is equal to it's equal to this. We worked that out already. So the probability that a randomly chosen person has a slow heart rate is that. So 0.1587. And in this last question, we just found that the probability of H given S is equal to 0.310. And we can see that these things are not equal to one another. So therefore, we can say that no, they are not independent of one another, just by doing this quick little check. So given that these things are not equal, they are not independent. Awesome. All right, moving forward. So next up, we need to find the probability that a random sample of 16 adults will contain exactly one person with a slow heart rate. Okay, so this time we're now taking a sample. So we've now got our population, we've taken a sample, our sample size is 16, and here we are interested in the likelihood that exactly one person will have a slow heart rate. So how can we put this symbolically? So yeah, we want to see if what the probability, so the probability that out of a sample of 16 people, only one of them will have a slow heart rate. So what are we doing here? Well, we're dealing with a binomial, first up, because someone either has a slow heart rate or they don't. So we should be thinking binomial CDF, binomial PDF. We're dealing with probability that they will contain exactly one person. So if we're just dealing with the probability that something is equal to, so that n is equal to a specific number, we're dealing with binomial PDF. Okay, so that's how we can work this one out. So jumping across to our calculator once again, we're going to go interactive, distribution, discrete, binomial PDF. We have x, so x here is the number that we're interested in, so we want x to be equal to 1. We want the number of trials here, that's 16, and the probability of success, that is going to be referring to the probability that somebody has a slow heart rate. That's what we've defined success as. And jumping back here, we know that the probability that someone has a slow heart rate is this number here, so that is 0.1587. If we hit enter here, that gives us the probability of success. So once again, that is binomial followed by x is equal to 1. So the number that we're interested in this case, that there is exactly one person. The total of number of people in this trial is 16, so that's our n value. And then lastly, we have the probability of success, which was this number here, and we can see that that comes out at about 0.190, correct to 3 decimal places. Just double check that that is correct. Yep, awesome. Okay, moving forward. So going across to II. Next up, we have for a random sample of 16 adults, we're going to say that the sample proportion, p hat, is the random variable that represents the proportion of people who have a slow heart rate. We want to find the probability that p hat is greater than 10%. So let's just go ahead and put that symbolically. So we're trying to find the probability that p hat is greater than 0.10. So what does that mean? Well, This here is the sample proportion. So if that is larger than 10%, remember P, well, our total sample is 16. Sorry, yeah, 16 here. So what we're trying to find out is what is the probability that H is greater than 10% of 16. Now, 10% of 16 is 1.6. So this is the same thing. We're just trying to work out the probability that the number of people with the slow heart rate is greater than 1.6. And of course, we can't have a decimal number of people. So this is just the same thing as asking what's the probability that that the number of people with a slow heart rate is greater than or equal to 2. So that's how we can work this out. So let's just go ahead and do that. So we're trying to work out now, once again, the sample of the number of people with a slow heart rate. That is a binomial because someone either has a slow heart rate or they do not. And this time we're interested in a range of values. So we're interested in, does the number of people with the slow heart rate, is it greater than 2? And at most, of course, can be 16. That would be everyone. So here we're doing a binomial CDF. And let's put in our inputs. So we don't need to remember the order of things. We can just go to the CAS. It is distributive, discrete, binomial CDF. Our lower bound is 2. Our upper bound is 16. Our number of trials is 16. And our probability of success is 0.1587, which is the likelihood that somebody has a slow heart rate. So putting that in, we get out an output of 0.747. So again, 3 decimal places. Is that correct? Where was I? Yep, that's correct. Awesome. Moving on. Okay, so I. For a random sample of n Mathsland adults, we're now told that p hat is the random variable that represents the proportion of people who have a slow heart rate. We need to find the value of n for which that sample, so the probability of that sample proportion is greater than 1 over n. Okay, this is a tricky one to kind of conceptualize. So first up, if we're talking about this sample proportion, if that sample proportion is greater than 1 over n, we're told that the number of people in our sample is n. So effectively, what we're saying here is that the probability, so if 1 out of n, if we have this, like the sample proportion is 1 out of n, that means that there is a total of 1 person in our overall sample that has a slow heart rate. So we want, what's the probability that 1 or more people in our sample has a slow heart rate? So effectively, we can write this p hat greater than 1 over n greater than 0.99. This is the same thing as saying the probability that the number of people with a slow heart rate is greater than 1. Because we're saying that the total number of people is n, so therefore that sample is 1 out of n, so therefore the number of people who have the slow heart rate must be greater than 1. Okay, so how can we write this a little bit easier? Well, it's really hard when you're dealing with effectively infinite number of people to work this out manually. We can't really work out the probability because if it's greater than 1, then it could be 1, it could be 2, it could be 3, it could be 4, it could be a bunch of things. But it is easier to work out 1 minus that, which is the complement of this. So the probability that h is larger than 1 is the same thing as the probability that h is less than or equal to 1. Okay. And if the number of people is less than or equal to 1, that means that the number of people is either 1, or 0, right? So the probability that h is equal to 0 plus the probability that h is equal to 1. They're the only 2 options here. So that's what we need to work out. Okay. Now let's think about it. So how can it be that the number of people who have a slow heart rate is equal to 0? Well, the probability that somebody has a slow heart rate, that is this thing here, and if all n of the people do not have a slow heart rate, then, well, what's the probability that 1 person doesn't have a slow heart rate? Well, it's going to be 1 minus the probability that they do. So the probability that they do is 1.0 0.1587, and the probability that everyone does not have a slow heart rate is 1 minus that to the power of n. Okay, so this is the same thing as the probability that the number of people with a slow heart rate is 0. So it's basically like every single person does not have a slow heart rate. So it's just 1 minus that to the power of n. Then we have, what's the probability that the number of people with a slow heart rate is 1? Well, if we think about it, if there is one person with a slow heart rate, then that means that everyone else does not have a slow heart rate. So that is n minus 1 people who do not have a slow heart rate, and one person, 0.1587, who does. Now, there are n possible people who could fall into that category. So we have n possible combinations for choosing that one person, which is the same as n choose 1. So we're trying to work out when is that greater than 0.99. We're going to do this in the CAS calculator. Can't do that by hand. So we're going to use the solve function. We're going to go solve 1 minus 0.1587 to the power of, to the power of, all right, to the power of n plus 0. So n times 1 minus 0.1587 to the power of n times 0.1587. We want to solve when is that equal to, so that was n minus 1 there. When is that equal to 0.99? And we're solving for n. I think I've forgotten a set of brackets there. There we go. So we're told, okay, obviously we ignore this negative solution. We're dealing with a whole number of people. The solution that the CAS spits out is this one here. So we can see here that using CAS, n must be, must be greater than 39 or 38.9 there. So we can see if n is greater than 38.9, because remember, these are exponents. So if we're raising to the power of n, and we've got like n must be, so for example, if n is equal to 38.9, then we put that here. This comes out as being equal to 0.99. If we make it greater than 38.9, then this will be even larger than this, which is going to give us a result that's larger than 0.99. So therefore, we're going to round up. So we can say that n must be equal to 39 people in order for the sample proportion to be greater than 0.99. All right. Lots of that question, so let's move on a little bit here. Okay, next up, we're dealing with the doctors take a large random sample of adults from the population and calculate an approximate 95% confidence interval. So let me just draw out what we're dealing with here. So what we should be thinking is, okay, we've got a normal distribution. And what do we know about normal distributions? Well, what we know is 95% of the data, or 95% of the area under a curve, is within 2 standard deviations of the mean. So if this here is our expected value, which is the same thing as the mean, the expected value of these sampler proportions, that must be plus or minus 2 standard deviations. The area under that curve between those two values, that must be equal to 0.95, okay? So let's just have a think about this range. So first up, the expected value, which is the same thing as the sample proportion in this case. We might remember this from the textbook. The sample proportion is equal to the expected value. That's going to occur right in the middle of this normal distribution. So if we're told here that the confidence interval was from 0.102 to 0.145, what we could do to work out what this expected value is just go 0.102 plus 0.145. That comes out as 0.247. Then to figure out what the center point is, so what's the point that's exactly halfway between those two, we can just take that number and divide it by 2. So therefore we can see that P must be equal to 0.247 divided by 2. That's equal to 0.1235. That's I. That's the answer. Now, explain why this confidence interval suggests that the proportion of adults with a slow heart rate in Statsville could be different to the proportion of people with a slow heart rate in Mathsland. So one thing that we can think about there is, okay, this is our expected value for the number of people in Maths Statsland. Yeah, this is the number of people. So the expected number of people with a slow heart rate in Statsville. If we compare that to the expected number of people with a slow heart rate in Mathsland, have we worked that out? Well, we know that the probability that a randomly chosen person has a slow heart rate is this, so 0.1587. So yeah, I think all we need to do here is we can just see that 0.1857, because that is actually outside of this little confidence interval, so we can see that is actually larger than this confidence interval here, we can say that therefore we're dealing with different normal distributions here. I think I'll come back to that one. That's yeah, it's because it's outside of the confidence interval there. What did I say before? Yeah, this is something that we haven't really covered so much in class, so I think we'll save this one for a little bit later. Yeah, it's just because it's outside the confidence interval. So we'll come back to that one. I think we'll have to move forward just in the interest of keeping this video on the shorter side. So moving on, this next question is a bit of a different context. So now we're dealing with a continuous random variable. We're dealing with a continuous distribution here. We've got these two functions. Now, whenever you have these functions, this one here, we're dealing with the time that it takes students to get to the top of a hill. This is the probability distribution function. To check if this is in fact a probability distribution function, it's always a good idea to check is the integral, so is the area under the curve from 0 to, in this case, infinity, of that function, is that equal to 0? So it's only going to be a valid probability function if it is equal to 0. So I'm just going to quickly type that in just to check this. So we have the integral from 0 up to infinity for the function 3 over 50 times x or t over 50 squared times by e to the power of negative x over 50 to the power of 3 integrating with respect to x. It is equal to 1, so it is good. Next, so we need to find the expected time in minutes of a randomly selected student making it to the top of the hill. So expected values when we're dealing with continuous random variables. This is one of those rules that we need to know. I believe it's on the formula sheet. The expected value is simply just going to be equal to the integral from 0 to infinity, or whatever the range is that you're dealing with, of that value, so of the variable t, multiplied by m t dt. So we can do this in the CAS calculator. Once again, we've got here the integral already. So I'm just going to multiply, like putting inside the integral here, another factor of x, hit enter, that comes out as this value here. So that is 44.6, and we give our answer here to 1 decimal place. So what this here represents is the expected time is about 44.6, or if we wanted to convert this to minutes and seconds, we can go interactive transformation DMS to DMS, type in answer, gives this one here. So this is the same as 44 minutes, because it's time in minutes, and 39 seconds. So this is the expected time. We're expecting most students, when they're hiking to the top of this mountain, it's going to take them about that amount of time. Now, we're told here that students who take less than this particular value, so 15 minutes to get to the top, are categorized as elite. We need to calculate the probability that a randomly selected student is elite. So what we could do to visualize this is we could graph this function. I've already done that just to save us a bit of time. So if I jump across to the graphs and table screen, I've typed in the function there. If I click to graph it, you can see this is what it looks like. It does in fact look like a normal distribution. So it's kind of like this sort of shape between those two values. So this here is the probability, that's mt, and over here we have t, and we want to find what's the probability that the time they take is less than or equal to 15. So in other words, we're trying to figure out what is the probability. So the probability that they are elites is equal to, so the probability that a randomly selected student is elite is equal to 0 to 15 for that function mt, integrated with respect to time. So going back over here, we can do that. So we're doing this integral from, let's just type it down here again. So that's 0 to 15 of dx comes out as this value here. So that is equal to 4 decimal places, 0.0266 to 4 decimal places. Okay, fantastic. All right, moving on to the next question. So last question now. So finally, we're dealing with the year 12 students at Mathsland Secondary College make up a total of 1/7 of the total number of students at the school. Of the year 12 students at Mathsland Secondary College, so this is the probability that the student is in year 12 and is elite. So of these people, 5% are elite. So yeah, so this is like the probability that they are in year 12. So year 12 and elite. So the probability that they are both in year 12 and elite is equal to 0.05. Or is that, no, that's the probability that they are elite given that, yes. So the probability that they are elite given that they are in year 12 is equal to 0.05 here. Okay, so we need to find the probability that a randomly selected non-year 12 student at Mathsland College is categorized as elite. So best to write out the question. We're trying to find the probability. So if we're dealing with a non-year 12 student, we can use the notation like not year 12 like this. So what's the probability that they are not in year 12 given that they're elite? So we can write it out as, let me have a think about this real quick. So it's like they are elite given that they're in year 12. Yeah. So, or given that they're not in year 12, I suppose. So we need to find the probability that they're elite given that they're not in year 12. Yes, like that. So to set that up, we need to know the probability that they're elite given that they are not in year 12, and that they're not in year 12, and divide that by the probability that they are not in year 12. Okay, so let's have a think about this. Filling in each of these probabilities. The probability that they're not in year 12 should be fairly easy to get. If we know that the total number of students is in year 12 is 1/7 of the overall population, the probability that they are not in year 12 is going to be 6/7 of the total population. And then we have the probability that they are elites and in year 12. So the way that we can think about that, we'll need to have a careful think about that. So the way I did it before was we can sort of think about these two sets. So we've got here the set of students who are elites and the set of students who are in year 12. If we were to break down these two sets, let's use a different color for this. So we're interested in the probability that the student is going to fall into this category here, where they are, where they are elite and not in year 12. So the people who are elite and not in year 12 are these ones over here. So how can we work that out? Well, that is equal to the probability that they are elites minus the probability that they are elites and in year 12? Yes, that would be it. So the probability that they are elites, we got that in the last question. So that's this number here. So that's 0.0266. The probability that they're elites and in year 12, that must be this value up here. So sorry about confusing you there. So of the year 12 students, 5% are elites. So this here, yeah, this is the probability that they are elites and in year 12. That's what I said earlier. Yeah. 5% are elite. Yeah. So it's the probability that they're elite and in year 12. Well, it's of the students who are in year 12. So I guess like if we were to select a random student, like what's the probability that they're in year 12? That is 1/7, the probability that they're in year 12. And then once we know that they're in year 12, the probability that they are elites is then 0.05. So we actually need to multiply it by 0.05. So that is the probability that they're elites given that they are in year 12. No, I was right that time. Yeah, so that is, probability that they're elite given that they're in year 12. Yeah. So anyway, so we're trying to work out the probability that they're elite and in year 12. Firstly, the probability that they're in year 12 is 1/7. Secondly, the probability that they are elite, given that we know that they're in year 12, is 0.05. So this would be how we would work it out. We would divide that by 6/7, type that into your calculator, you'll get the answer. Looks like only 0.2% or 2% of people, 20%, sorry, got this right. So it's not just me who's struggling here. But let's just type it in. So first up, we've got here the answer minus 1/7 times 0.05. Divide that by 6/7. Hit enter. Comes out as the answer is equal to this here. So turns out that the answer is 0.22, 0.022, and that would be the probability that we're expecting here. And that's it. Awesome. Okay, so obviously quite a lot in this video, so hopefully you kept up with that, but if you're stuck on anything, please let me know. All right, I'll see you in class. Have a good one.